Because this question related to one of the questions in our second homework assignment. Yeah. So you will have Q initial condition, I initial condition, how to solve the problem, right? Yeah. So there are two ways we can, find the C1, C2. Yeah. All right. The first way, remember our original equation. So let's go back to our original equation. L times I prime plus RI plus Q over C equals E of T, right? That's our original equation. Yeah. So we need to start from this equation. Okay? This equation, we calculate t equals 0 value. Yeah, plug in t equals 0, both sides. Okay? Yeah? E function, you plug in, you can find a value, right? Q, is that Q of 0 initial value? Yeah, so this term is gone. I, but you need to calculate I. I derivative, because your I equals IP, IH plus IP, right? Yeah. And IH, IP, you have the form, at least you have the form. So can you calculate I prime of 0? I prime of 0, you can use here. Yeah. Right? Yeah? Yeah. Then you get a second equation. In this way, you get a second equation. So that's one. Another, you can use the Q version, right? Yeah? So remember, we have a Q version. LQ double prime plus RQ prime plus Q over C equals E function. Yeah, we use this version. This second order ODE, this time we have initial condition Q, but the I is Q prime, right? Yeah. So we can Q prime of 0 also equal to 0. That can be solved. Yeah. So these two ways we can use to find the final solution. Okay. Yeah. All right. So So here just let you know which way. Yeah. If I can find time, I may complete the solution using these two ways. But I need to put it behind other important things with higher priorities. The first one, I need to finish grading your homework assignment. That's the highest priority. Second, I need to give you homework assignment number 2. Now, after that, so then I do this. For your interest, All right, so we complete the whole module 2. Now we need to start module 3. Oops, sorry. I don't, I keep this. Nice. All right. Module 3. New topic. Higher order linear ODEs and more Laplace transform. Yeah. First, the higher order ODE, yeah, because after we have the results of second order, then we just generalize our results from second order ODE to higher order ODE. Yeah. So pretty straightforward, the generalization part. Yeah. Then, more Laplace transform, there is another important part of the knowledge of Laplace transform we need to learn. Yeah. A Dirac function. Yeah. After we learn the Heaviside function, yeah. Heaviside function very useful. Another function, Dirac function, also very useful. So we need to complete that part. Yeah. And also another operation, special operation, convolution. Yeah. Convolution operation related to Laplace transform. So those two topics we need to learn in Module 3. Yeah. Then we pretty much complete the whole Laplace transform topic. Yeah. All right. Yeah. First, Part A, higher order linear ODE. Yeah. 8.1, basic types of higher order ODEs. Yeah. Right. So let's look at the general form of nth order ODEs. Yeah. Yeah. Capital function, yeah. So very general. Yeah. So here you can see this capital F function, you can treat it as a multivariable function. Yeah. So x, y, y prime, yeah. So it takes a position of a variable. Yeah. So although it relates to y with derivative, yeah, but actually you can treat it as a multivariable function. No? Yeah. Yeah. For example, yeah, you have, so this function you can view in this way. Yeah. You have x0, x1, x2, right? Yeah. xn. This is a normal multivariable function. Yeah. Now, you just, do some substitution, simple substitution. Yeah. Replace x0 by x, x1 by y, x2 by y prime, and so on. Yeah. Yeah. So you treat in that way. Yeah. All right. This is the general form. Yeah. All right. Yeah. So the way we study the higher order ODEs, we extend the results for second order ODE to nth order ODE. Yeah. So the results we learned in Module 2, well, we can easily extend them to nth order ODE. Yeah. Types, yeah. So the types, yeah. First type, basic ODE type, standard form of linear ODEs. Yeah. Yeah. So that's a generalization of second order. Yeah. But this time we use, all these P functions, P1, P2 through Pn-1, all these functions that are functions. Yeah. Simple generalization. Yeah. All right. So the non-homogeneous linear ODEs. Yeah. This form. Type 2, those ODEs that can be represented by the general form ODEs. Yeah. Yeah, because sometimes we may not be able to get the standard form. Yeah. So there, we can only take the general form. Yeah. All right. But cannot be, standard form. Yeah. So that kind of equation will be harder. Yeah. The general form ODEs will be harder than the standard form of linear ODEs. Yeah. Type 3, yeah, homogeneous linear ODEs. Yeah. Yeah. Because the solutions, yeah, closely related, right? Yeah. So the H part, the particular part, yeah, so closely related. Yeah, so we need to study these two types together. Yeah. All right. Type 4, initial value problems. Yeah. Yeah. Adding initial conditions. Yeah. Yeah. So we need a sufficient initial condition in order to get a final solution, unique solution, right? Yeah, because our goal in our application problems, we want to find a unique solution. Yeah. Only under this kind of initial conditions, we can get a unique solution. Yeah. All right. Yeah, so that's the basic ODE types. Yeah. All right. Yeah, all right. Next, 8.2, basics of solutions and linear independence. Yeah, so for this part, we want to generalize our second order ODE. Important results for our second order ODE to the nth order ODEs. Yeah, linear ODEs. Linear. Yeah. If it's a nonlinear, yeah, the general form not necessarily linear, right? Yeah. Standard form, yeah, so that's the linear. Yeah. But general form nonlinear, yeah, so we do not have a lot of results. Yeah. Very hard to study. So the main results all about linear ODEs. Yeah. All right. Yeah. Let's look at the existence uniqueness theorem, generalized to nth order ODE. Yeah. First, homogeneous version. Yeah. Yeah. All right. With initial conditions. Yeah. All right. Yeah. For some open interval I. Yeah. All right. If the coefficients, all these p functions, are continuous on I. Yeah, that's the same as the second order. Yeah, we require PQ functions continuous on I. Here, we require all these P functions continuous on I. Then, we have the conclusion. The initial value problem has unique solution y of x on I. Yeah. Yeah. Pretty simple. Yeah. Yeah. Has unique, for has, that's existence, right? Yeah. Must have a solution. Second, the solution must be unique. Yeah. So both existence and uniqueness. Yeah. Yeah. Generalization from second order. It can be proved. But here we do not need to, spend time on the proof. Yeah. Then another simple, straightforward generalization, superposition principle, homogeneous. So we have this superposition principle, linearity principle also, yeah. Sums and constant multiples of solutions. So we call linear combination, right? Yeah. So here, so this phrase, sums and constant multiples of solutions, that's our linear combination concept. Yeah. Okay. Yeah. Yeah. So here I have to write linear combination concept. So we generalize the linear combination concept from two elements to, here, how many elements? Yeah. Nth order, right? Nth order, so our solutions, we should have n solutions, right? Yeah. Because second order, we have y1, y2, two linearly independent solutions. So here, nth order, we should have n linearly independent solutions. So here, linear combination of n linearly independent solutions. Yeah. Some, yeah, but yeah, so, for above homogeneous, yeah, also solutions on I. Yeah. So that's another result. Yeah. This principle does not hold, yeah, non-homogeneous, non-linear ODEs. Yeah. But remember, for our second order, yeah. So this statement also true for our second order ODEs, homogeneous or nonlinear. Yeah. So here we consider homogeneous. Yeah. Yeah. We do not because nonlinear, we cannot do anything, right? Nonlinear, we cannot do anything. But here, let's just consider non-homogeneous but linear. Yeah, linear. Okay? We consider that case. Yeah. Can we do something similar to second order? So second order, although linear combination won't be a solution, right? But remember, I talk about linear interpolation will be the solution, right? When we do linear interpolation, we will get another solution. Yeah. So here the question, can we have the similar concept of the generalization to that linear interpolation concept to this nth order? Yeah. Yeah. Actually, we have. Yeah. We have the similar. Yeah. But we do not call linear interpolation in this case. Yeah. Yeah, because linear interpolation, that's for two elements. We do linear interpolation. For more than two, yeah. Because linear interpolation is based on the geometry, right? Geometry. So line segment, you interpolate, between 2 points. That's the linear interpolation. Yeah. So for more than 2 points, yeah, the dimension, you consider multi-dimensional situation, and there is a similar concept, but people do not call linear interpolation. Yeah. Right? Yeah. So there is other concept. Yeah. So here, remember, when we consider linear combination, we use constant k1 times y1 plus k2 times y2 plus kn times yn. This is a linear combination, right? Yeah. So this linear combination, if you consider that for the non-homogeneous case, in general, not a solution. Okay? Not in general, not a solution. Okay? All right. But, yeah, so here, the special case. Okay. But, for the case, what case? The case, sum of k1, k2, sum of all the k coefficient equals to what? Think about that. All equal to what? Okay? Yeah? Yeah. This is the way we generalize that in linear interpolation, right? Yeah? Sum of the two coefficients equals 1. That's the linear interpolation of second order case. Yeah, but here, so we do not use linear interpolation concept. But the condition still, sum of all the k coefficients equal to 1, then you add them together, right? Yeah? So you get the same solution. Yeah. Think about that. Because the right-hand side, because the right-hand side, you have R function, yeah? You have R function, yeah? K1 times R function, K2 times R function, because right-hand side are all R function, right? Yeah. K something times R function. You add them together, you get you get R function. Yeah, 1. Yeah. So with this extra condition, you also get a solution. Yeah. But nonlinear, so we have nothing. Nonlinear, so yeah. We cannot do anything on nonlinear case. Yeah. All right. So that's the generalization. Yeah. Linear independence and dependent. Yeah. So this generalization. Yeah. Wronskian, we generalize to n-dimensional case, yeah, or n solution case. Yeah. All right. We call y1 linearly independent on I if the equation k1 y1 through kn yn equal to 0 on I implies that all the k of coefficients must be 0. That's linearly independent. Yeah. Yeah. So linearly independence forces. Yeah. If you have this condition, it forces all the k coefficients must be 0. Yeah. That's linearly independence. All right. Yeah. So then dependent, yeah, so they are linearly dependent. Yeah. Then, so this linear combination, the function of linear combination of n y functions equal to 0 on I holds for some k1, all these nk coefficients, not all 0. Yeah. Some of them could be 0, yeah, but not all 0. Yeah. If you have that set of k coefficients, then we call these n functions are linearly dependent. Yeah. So here, not all 0. Yeah. Yeah. All right, so that's the generalization. So then the Wronskian, yeah. So the Wronskian we can, yeah, because for this equation we can take first derivative, second derivative, yeah, because so think about, yeah. So this function equal to 0 or non-zero, yeah. So yeah, because both cases we'll consider equal to 0, right? Yeah. So the independent case, dependent case, both cases, we consider this linear combination function equal to 0. Then, if equal to 0, we can take because the function equal to 0 is on every point on I, right? Yeah, I is the interval. Yeah. So not just one point in I, so all the points in I interval. Then, the derivative function also equal to 0 on I. Second derivative function also equal to 0 on I, and so on. Through nth derivative of this function also equal to 0 on I. Yeah? So based on that, so if we calculate the Wronskian as the determinant, yeah, so of this n by n matrix, right? Number of rows, n rows. Number of columns, n columns. Yeah. So it's an n by n matrix. Yeah. So we define this, the determinant of this matrix. That's the Wronskian of these n y functions. Yeah. All right. Then we can make conclusion related to these two concepts, linear dependence and linear independence concept. Yeah. First case, these n y functions are linearly dependent. Okay, now we talk about dependent first. Dependent on I if and only if W is the determinant. Okay? W identical to 0 on whole interval I. Yeah. Identical. Yeah. That means there is no point inside I interval such that this W function, W is a function, W function is non-zero. No such point. Yeah. So that's identical to 0. Yeah. All right. So that's the linearly dependent case. Linearly independent case. Yeah. On I, if and only if W not equal to 0 for some point, just the 1 point. Okay. If it's for 1 point in I to make this W, yeah, the Wronskian, yeah, because it's a function. If you calculate the determinant, you get a function. So this function, if you can find 1 point W of x1 not equal to not equal to 0, then linearly independent. Yeah. That's a generalization, yeah, from second order case. Yeah. Yeah. So these two conclusions, if we look at from linear algebra, yeah, so pretty straightforward. Yeah. Yeah. Linear algebra. Yeah. Here I do not, repeat that story. No, linear algebra. Okay. Yeah. The matrix, the unknown K is a vector, n-dimensional vector. Yeah. So that homogeneous equation. That story I skip. Yeah. I just give you the results, generalization results here. Yeah. Yeah. But later, yeah. Although I skip here, yeah. But later, because we will solve ODE of linear systems. Yeah. So we have a block we need to study. Yeah. So that's the solving ODE of linear systems. Yeah. Yeah. At that time, I need to review a lot of linear algebra results. Yeah. So something I skipped here. So that part. So I will go through. And review a little bit. Yeah. Yeah. So here we do not need to spend much time, yeah, on linear algebra. Yeah, because that part is also important for this class. Yeah. All right. Third, here let's look at a few examples. Yeah. Yeah. Third order Euler-Cauchy equation, part 1. So let's solve initial value problem. It's a straightforward generalization of second order. Second order, we saw the Euler-Cauchy equation. Yeah. But here, third order, yeah. Same idea. Yeah. The solution, we take the special form, power function form, y equals x to the m. Yeah. M, undetermined parameter, non-necessary integer, Yeah. All right. So when we do that, yeah, because the special structure of this equation, we can take advantage of the structure of the original equation if we use the power function form for our solution. Yeah. So you will see it. Yeah. All right. So we calculate, yeah, all the derivatives. Then we plug in, yeah, and do some simplification. You can see, yeah. So the reason we can take advantage because you can look at all the terms contains the common factor x to the n. Yeah. Each term, yeah, yeah, yeah. So the structure, just perfect for for the, common factor property. Yeah. So then we can cancel out, right? Yeah. So this x to the m. So this term, common factor, we can cancel out both sides. Yeah. So we get a cubic. So this is a cubic equation about m variable. M variable. Yeah. Yeah. So then after simplification, so we get a cubic equation. Simple cubic equation here. And then, do you know how to solve this? Yeah. For quadratic equation, we have quadratic formula, right? Yeah. But if I ask you to solve this cubic equation, how do you solve it? Yeah. You're allowed to use calculator. So there is a powerful calculator online, calculator called Wolfram Alpha. So if you type this equation in Wolfram Alpha, it can solve it easily. It can do factorization. First, it will factorize the left-hand side. Yeah, although here I do some manual manipulation. Yeah, but if you use calculator, you get a result directly. So here I still because when human do this, we'll do some manipulation to factorize the left-hand side cubic polynomial. Yeah. So at the end you get this factorization. Yeah, there is some technique, okay? Yeah, but for you, I do not require you master the factorization technique. Yeah. So I allow you to use online calculators. Yeah. So you get a result directly. Yeah. All right. Then 3 roots, single root. Here, single root. So you have 3 solutions. Y1 solution equals x. Y2 solution equals x squared. Y3 solution equals x cubed. So you solve the problem. All right. Yeah. But here, in this example, I try to give you good numbers. Now, so when we choose the coefficients, so I like to let you find nice numbers for m variable. Yeah. But in general, you may not have the nice numbers. Yeah. Especially in the real world applications. Yeah. The number usually, most of the time, not a good looking numbers. Yeah. Not good looking numbers. Very messy. Yeah. Very messy. Yeah. And another case is you may have complex solutions, right? Yeah. Not necessarily real solutions. You may have complex solutions. Yeah. Yeah. So you need to write your y1, y2, y3. Even you have complex solutions, you need to write y1, y2, y2 solutions. Yeah. But in that situation, our y1, y2, y3, 3 solutions, all real functions. Yeah. Remember, in our second order case, even we have two complex solutions, we get 2 real solutions. Yeah. So the same way, we can get real solutions. Yeah. Yeah. All right. That's the first example. Second example. Yes. Yeah. All right. Yeah. So this time, okay, continued. Yeah. All right. Yeah. So not a second. Yeah. So because we need to write a general solution, right? Yeah. C1 linear combination, C1, C2, C3. constants. Yeah. But when we write the general solution, yeah, this is a general solution this way. How do you know these three solutions are linearly independent, right? X squared, x cubed. These three solutions are linearly independent. Yeah. If they are linearly independent, yeah, so why it is important? So here, first, I review the question. Why linearly independence of these three solutions is important? Yeah. First, answer this question. Because if we have three linearly independent solutions, then these three solutions form a basis of the whole solution space. Basis, here. So we generalize the concept basis from second order to this higher order. Basis, okay? Yeah, the basis concept is important here. Another important reason we use basis, we require our three solutions form a basis, is because if we have a basis, we use a linear combination of three basis functions, we can cover all the possible solutions of this equation. We won't miss anyone. If they do not form a basis, then you may miss some of the solutions. You cannot cover all of them. You will miss part of it. So that's why we really want to make sure we get all the basis solutions. So here we need to check independence. If they are linearly independent, then we know they are basis. All right, to check. All right, so what's that? First, second row to, because initial values, right? Yeah. So here we need to, make it satisfy initial values. So we need to solve these little c coefficients, C1, C2, C3, following three conditions, so we get a linear system, 3 by 3 linear system. Yeah, so we can solve this linear system easily. Yeah. So for you still use that Wolfram alpha to solve. Okay. Yeah. Yeah. So very easy, very fast. Okay. You do not need to. So if you really want to challenge yourself, you can solve, manually on your scratch paper. Yeah, but no problem. Use the calculator. Yeah, the current calculator very powerful. Yeah. All right. So you get a final solution. Yeah. But we like to check the linear independence. Right? Yeah. Make sure we get a basis. Yeah. All right. Yeah. So we calculate the Wronskian. Yeah. So the Wronskian for 3 by 3 matrix. Yeah. So I hope you know how to calculate the determinant, 3 by 3 determinant. Yeah. I will not ask you to calculate even 3 by 3 determinant. You can use the Wolfram alpha to calculate, right? Yeah. Yeah. But if you know how to calculate manually, that's a plus. Okay. Yeah. Yeah. But so you can use that. So here I just show you the technique, calculating technique. Yeah, here, so a lot of transformation steps. Yeah, yeah. So then at the end you get this polynomial. Yeah. This polynomial, based on our generalized result, if this polynomial is non-zero at one point in the interval x1, we only need 1 point, right? That linearly independent. Let's say x equal to 1. Yeah, because to make this polynomial 0, x only 2 possibilities. One is x equal to 0, another x equal to 3/4. 3/4, only these 2 points, this polynomial equal to 0. But for non-zero, all other points make this polynomial non-zero. Yeah. But for our result, we only need x1, 1 point, non-zero. Then all the 3 functions are linearly independent. Yeah. All right. Yeah. So that's some review a little bit. Yeah. All right. Yeah. So here. Yeah, so we rewrite. Yeah. So rewrite. Yeah. Here in this case, x cannot be 0, right? If we write this way, x is not allowed to be 0. But in this case, x is allowed to be 0, right? Yeah, because you don't need to do division by 0 in the original form. But in this converted form, yeah, x is not allowed to be 0. Yeah. All right. The general solutions. Yeah. Yeah. So here we talk about homogeneous for nth order, the general solutions. We want to generalize the result for this case. All right. Yeah. Existence of a general solution. If the coefficients, all these p functions, are continuous here, yeah. Yeah. Similar to our order 2 case, continuous on some open interval I, then the equation has a general solution, existence of the solution on I. Yeah, so simple. Yeah, continuous. Yeah. Yeah. Existence. All right. Then, yeah. So this second result, yeah, also generalization from order 2 case. If the ODE2, so the above, I copy the ODE2 above. Yeah. Yeah. So if you do not, if you ask yourself which one is ODE2, so I put a number there. If the ODE2 has continuous coefficients on some open interval I, then every solution little y, so this time we want to cover all the solutions. Yeah, this second result, we want to consider little y equals capital Y of 2. Yeah, so this capital, what's capital? The definition of capital Y is linear combinations of all these n solutions of the original ODE. Yeah, where these n solutions must be a basis of solutions of 2. Yeah. So here the importance of the basis. Yeah. All right. Then, so here, that suitable constant. Yeah. So here, another thing is every solution. Yeah. So this I emphasize this part. Every solution can be represented as a linear combination of n basis functions. What's that? What's the meaning of that? Yeah. So this general solution covers all the possible solutions. That's the significance of this result. No missing one. Yeah. All covered in this general solution. Yeah. It's a generalized result. In other words, so there is another, my remote control. Oh, there. Yeah. Yeah. Another. Yeah. Why I emphasize all covered? Yeah, because there is another concept. Yeah. Singular solution concept. Okay. If this general solution covers all the solutions, that means no singular solutions for this type of ODE. So what's the singular? Yeah. Oh, sorry. Yeah. The singular solution. Remember? Yeah. Singular solution. Singular solution. That's a special solution that cannot be derived from the general solution. That's the concept of singular solution. Yeah. Yeah. So no way you can, by choosing special constant C1, C2, Cn, to get a singular solution. No, that singular. Yeah. It follows different rules, patterns, things. Yeah. Yeah. Example, remember the logistic equation. Yeah. When we solve the first order logistic equations, we saw the singular solution example. Yeah. Yeah. All right, so here I just refresh your memory. Yeah. All right. Yeah. So then, so we complete this part, right? Yeah. Yeah, because next 8.3, so we have 2 topics left, 8.3, 8.4. So we leave next time. Yeah. Next time, after we finish these 2 topics, we need to start part B. Yeah. Part B. Yeah. Laplace transform on that Dirac function. Yeah. So that's another important topic. Yeah. Dirac function. All right, that's it. Yeah.